clarified, yeah. Perfect. Okay, so it's an honor to introduce our second keynote today, Jitendra Malik, who's the Arthur J. Chick Professor at Berkeley. He's a leading researcher in computer vision, robotics, machine learning, and has changed really how we think about machine perception broadly. Many honors, of course. Among them, I think I'll highlight a member of the National Academy of Sciences, Academy of Engineering, and most recently, if I know, Fellow of Royal Society, right? That's the most recent one. So congratulations on that. I always like to highlight mentoring. So he's mentored, over 80 PhD students and postdocs at this point. I know many academic children and grandchildren are in the room and among leadership in our field and many other fields. So with that, welcome.
Thank you so much. Thank you for the kind introduction and the organizers for inviting me. So I'm going to talk about robot learning and a particular take on robot learning. But let's start with what are the key problems in robotics. So everybody likes to do everything in threes. So these are my three, which is navigation, locomotion, and manipulation as umbrella terms under which a lot of robotics can be construed. So let's see what can we do in navigation today. And I'm going to talk about this paper from a couple of years now. And hopefully this just plays. Okay. So the task is what I call the Airbnb task. So the task was, we have so many, now practically decades of work on SLAM and navigation and path planning and object recognition and so on. So let's put it all together and see if we can solve the following problem. And this is how I articulated it to the folks on my team. You rent an Airbnb. You walk into the door, you put your robot down, and then you tell the robot, go find a sofa or go find a television. And it has to go find it. In the course of doing that, it's going to build some representation, which will be a partial map of some sort. And of course, it's going to rely on visual recognition, because how do you know whether you have come to a TV set? So goals can be specified in a variety of ways. They could be specified by language, they could be specified by picture, and this is what you have to do. Okay, and now let's see what it can do. So what you'll see is that there is an observation for this robot. What's in the camera view, that's what you see at the top left. And then it's also been given some target, which will be shown shortly. And then it goes from one target to the next, which a human is specifying. Okay, so, and then a map is being built, that's being shown here. And then it's given a certain target, which you should see now. Okay, so the target is that photo of a sink. So it's roaming around, it has found various objects which it has put into its map. So this is like the memory. It's a spatial map together with some semantics. And then once it's found, it's had success, then you give it another target and so on and so forth. And this actually works. Okay. And there are follow-up work on this. And generally, I regard the problem of navigation as one of the great successes of both work in computer vision and in robotics. And interestingly, what does not work well is if you try to do it by end-to-end training, because you do it in a simulator and you'll end up overfitting and your vision doesn't work well. Vision systems to be trained have to be trained on a very large variety of real-world data. Okay, so that's navigation. In fact, we tested it on these 200 different goals in multiple apartments, et cetera, et cetera. So I feel reasonably confident about this. If you had an application which relied on navigation, we can do this. Okay, now let's talk about locomotion, and in particular legged locomotion. This is also a field which has many decades of work, earlier largely in the model-based control paradigm, and more recently in the paradigm of reinforcement learning. The basic setup is you do reinforcement learning in simulation because your robot cannot afford to fall down so many times. And initially we did this for quadrupeds, and now for humanoids, and I'll just show you some results. So this is, Digit walking around in the hills of Berkeley, in the neighborhood of Berkeley. And it can go on for, until your battery life runs out. Okay. More challenging tasks are hills. San Francisco, we live near San Francisco, so you have to show off in San Francisco. And so this was steep, but I was talking with Ilya, and then we wanted to make sure that we could actually walk on the steepest hill. So Ilya did these experiments. So this is in fact the steepest hill in San Francisco, if Google and Wikipedia are to be believed. And there we can do that too. So again, I feel and this was a couple of years ago, and many people have replicated this line of work. So I think we should declare that legged locomotion with this general paradigm of reinforcement learning in a physics simulator, and then basically zero shot in the real world. This works. I think this is kind of a reliable result. And I mean, you've seen there have been demos from Unitree at the Chinese New Year, where they had lots of these robots and performing various kinds of parkour type tasks. Okay. So where do we stand in robotics today? So I'm arguing that locomotion and navigation are kind of success stories, and in manipulation, there's a long way to go. And if we think of it as an analogy with language and vision, where language and vision I regard as we've had real big success in the current machine learning paradigm. And if you say, okay, let's apply that same paradigm to robotics, then you would need to have lots and lots of data. And it's not easy. That paradigm in that vanilla form is not going to work, is what I'll argue. And think about what would be the right data. So the right data would be recordings of my sensory motor state. What do I see at every moment in time, and what commands do I issue to my muscles? And we don't go around uploading that kind of data to the web. Whereas, in fact, all the books are on the web, and there are 1 trillion photos on the web, and 156 million hours of video is on YouTube and so on. But we don't have our sensory motor experiences on the web. And even if we did, my sensory motor world is not the same as that of a robot. So there would be an embodiment gap. So the straightforward way of thinking about this is, I think, not going to work. Okay. So we need to be a bit more sophisticated about it. There's one insight here, which is that LLMs have got away with being much more data hungry than humans. So there's a factor of 10,000. There's a typical estimate given the number of, so like a 10-year-old child has heard like 100 million words, and they are perfectly competent at language. Our LLMs need much more data, like 1 trillion. So that's a factor of 10,000 there. And so there is an inefficiency there. And I already said that the data problem is bad, and if you have, so maybe this inefficiency is something which we can think about, and if we find cleverer ways of building our models, we may not, we may still be able to make the problem tractable. So that's a challenge. Okay, so I want to start with a high-level view of how I think about robotics. I mean, this is not unique to me. This idea, general idea, probably goes back decades. I mean, if people talked about task and motion planning, and those are variations of the same idea. But I think sometimes people forget this in the current era, so I want to recap this. So I want to argue that there are 3 levels at which we have to consider robotic manipulation, and all 3 levels are important. You cannot hope to ignore any one of them. Let's get into examples. So essentially it's high level to low level with these three tiers. So let's talk about the level of goals and plans. So goals and plans, okay, simple. Let's say my task is to make an omelette. And I can type this command to Google Gemini, and in fact I did, and this is the output. So this is great. This is the problem which can be solved by LLMs. Now there's a sentence in there which is, crack eggs into the bowl. Now this is where your LLM is not going to help you, right? Cracking eggs into the bowl is a physical act, and you sort of have to solve this problem at the physical level. And that's where things are going to fall apart, okay? I mean, we can have very sophisticated LLMs and VLMs or whatever, but ultimately these actions which have to be grounded in the physical reality. So I have a way to emphasize this, which is that every action corresponds to some movement in the physical world, and there is a goal. And both levels are important. So the LLM emphasizes, or language in general emphasizes, goals and plans. But movement in space and time is equally important. And language is not used for that. Language is used for compressed communication. You do not describe trajectories in X, Y, Z coordinates over time. That's simply not the way we use language for. So in fact, my slogan is, I mean, there's the top level of goals and plans is really the level of Aristotle. Because in fact, and I mean that quite seriously, because there was a so-called general problem solver developed by Newell and Simon back in the 60s. And that did something called means-ends analysis. I'm trying to solve a goal. What are the sub-goals? Let's solve them, et cetera, et cetera. And this, in fact, goes back to Aristotle and Nicomachean ethics and means-ends analysis. So it is a level of Aristotle. But of course, now we can do it with Gemini, but it's that idea. This is what I mean by trajectories, right? So let's say at the level of 1 or 2 seconds of time, these are all the kinds of trajectories we do. They involve you're moving your hands and interacting with objects and so on and so forth. So these are trajectories in 4D, right? So there's clearly a level there of analysis which makes sense. But this is not all. So we can call this the level of Euclid, right? Geometry, kinematics would be the term from robotics. But there's another level, which is the level of forces. I mean, Newton, F equals ma, right? So suppose I want to pick up this object and lift it. I'm going to apply some grip force. I have to have enough force so that the object doesn't slip down. So the friction needs to compensate for gravity and so on and so forth. And these are, each of these one-dimensional plots corresponds to some variable which is being plotted over time. And at the bottom, you have the associated sensory signals. So in the case of humans, in our fingers, we have tactile sensing. So we have these, and these are firing when you are pressing on the object, and they're telling you how much force you are applying. And then if it slips, you apply more force, et cetera, et cetera. So there is a very fast sensory motor loop involving tactile and proprioception, which is being used to quickly adjust for when the state changes. So in my view, this level is equally important. So these are the 3 levels that we need to care about. And any story that somebody constructs about robotics, if it doesn't treat all these 3 levels seriously, is not going to work. I think we have to accept that and work with that. Next, I want to just state a religious belief for me. And so I'm using the term credo consciously, right? So for me, it's a religious belief that the long-term future of robotics requires dealing with multi-fingered hands. In the short run, parallel jaw grippers have been very effective and are being used all over the place. But I personally, the research that I'm interested in is about multi-fingered hands. And here's the logic. I mean, these are all various tasks that and demos that a student of mine, Torulin, collected. And these were all tasks where essentially parallel jaw grippers are not adequate. You really want multi-fingered hands. If you have this very fancy bottle of wine, you don't want to be touching it at just 2 points of contact. You'd rather have the solidity of a multi-finger hand grasp, etc., etc. So I think that we can argue this. I'm just defining the problem which I'm most interested in, which is multi-fingered hands. Okay, so now we return to the central question, which is how should we train robots? How do we design controllers for robots? And of all these levels are going to be necessary. I would argue that our focus largely has to be on the second and third levels, the middle and lower level. The top one, there are adequate solutions around. I don't want to waste too much time thinking about that. How should we train robots? And I'm going to give you some opinionated commentary. And so one first remark is robotics is well behind NLP and computer vision, and this is because of the shortage of data. Now, these are the 3 leading data sources that people have come to believe in. I will argue that each of them has some pluses and minuses, and let's analyze them critically. So the first one is teleoperation. So let's play this out. So this is the dominant paradigm today for collecting manipulation data. It's largely in the context of parallel jaw grippers. But what you're doing here is that the human is, so these configurations are called leader, follower, or master, slave, or whatever you want to call it. And then the human does something and the robot does exactly the same thing. And you can record the full trajectory. So you've got the kinematics, dynamics, et cetera, et cetera. Everything is recorded. Now, it's a difficult task for the human to do because the human is not getting any haptic feedback. So the human is relying on vision. So vision is always slow, right? Vision always adds like 200 milliseconds of delay. So the human vision system is what is adding the delay here. So the net is, yes, you can collect trajectories like this, and in fact, millions of hours of this data is now being collected all over the world. Right now, there are probably thousands of stations where this sort of data is being collected. Okay, and in a certain sense, this paradigm is easy because you collect trajectories this way, and then you just distill them into a policy. Okay, it's supervised learning. It's just kind of rote learning and replay of that trajectory, which is easy to do. So if you are a startup and you want to show results in 3 months, I mean, this is the way you should proceed. But what are the limitations? So first is that there are human sensory motor limitations. Humans can do the task because humans are amazing and they can learn it, but I have tried to do this. It's very hard. It actually is like a learning problem. You have to somehow, learning as in human learning, you're trying to become skilled at this. And then there's a second, so that's like the fundamental problem. If I want to be very critical, the way I think about it is, it's like tying a horse to a car, right? The car by itself can move fast and the horse by itself can move fast. You tie the two of them together. So the human could do a task very fast. The robot could do the task fast because it's got its own motors and so on. You put the two of them together, you've got the slowness of the human imposed on the robot, and the human is not operating at their best either. Okay, there's a domain gap between training and test conditions because all the scaling laws that we talk about, they work. I mean, in the language setting, they work. And they are conditioned on the fact that when you have more and more data, you're dealing with more and more edge cases. But the way we collect data for these robots are usually in work cells that we have constructed. So it's not clear to me that more and more data is getting you that kind of diversity that will deal with the edge cases. Okay, so anyway, this is my critique. I think these are, at least the first argument is a fundamental argument. It can be, the only compensation for that would be to design much fancier teleoperation systems with haptic feedback and so on. But those will be much more expensive. So those are not what I use today. Okay, let's go to the second paradigm, which is common, which is learning from video. So this is egocentric video. It could be exocentric video. And the idea is you have humans doing the tasks. So a clear plus for this is that the humans are acting like humans, so it's much more natural. And of course, thousands and millions of hours of this kind of data is being collected too. So as a computer vision person, this comes very naturally to me that this is the way we should be doing this. But I should acknowledge that there are some challenges here too. So the first one is that this is data for a human, which is not the same as a robot. So there's an embodiment gap, and we'll have to find a way to deal with it. Second issue is that there is missing information about contact. So there's only partial observation. You do not get full state information. You know the kinematics, as it were, but you don't know the dynamics. You don't know what torques are being, well, in here it'll be like muscle activations are being applied. We don't know that. Okay, then let's get to paradigm 3. This is simulation. So simulation essentially this is a physics simulator. So Mujoko, Isaac, Newton, I mean, these are some of the names. And this paradigm has worked for teaching legged locomotion. Legged locomotion is a success story, and it was driven by reinforcement learning and simulation. So we define a control problem, an optimal control problem with certain reward terms, and then we find the solution through RL, which is a fancy way of doing trial and error. But we get good trajectories and good policies, and it works. And what's the critique? So one standard critique is the sim to real gap, that the physics in the simulator is not, I mean, the talk just before mine was talking about issues like that, the last 2 talks, in fact. The sim to real gap. And then there is a second point which is slightly more subtle, but in practice this is as much of a bottleneck, which is that we specify the task by specifying the reward terms, and this is a pain. So here's a simple task. So this is based on work in my lab. I mean, these are some of the authors of the paper. So you're trying to do something simple like pouring water. Okay, and how do you specify, how do you tell the machine that this is what you want to do? So you write down various reward terms, okay, and these are some of the kinds of reward terms, and this gets tedious. Okay, we had to do this in locomotion, but there we were lucky. A relatively few terms which captured forward movement, energy conservation, smoothness, that was good enough. Here, there is a lot of this engineering, and plus you have to do it separately for each task. One is for pouring water, one is for inserting a thread into a needle, and so on. So this is actually one of the key reasons why people really jumped at behavior cloning, which is the technique used on top of the teleoperation data. Because you don't have to specify the task to a human with all these terms. You just tell a human, pour water from a jug into a glass, and that's good enough for them. And then they do the task, and you collected the trajectories, and then that's it. So the trajectories are what you work with, and you don't have to do all this painful reward engineering. So this is, I think, why the BC and teleop paradigm took off is that it is actually very easy. The reward specification goes away, problem goes away, and because you're communicating to a human, you don't have to communicate to a computer, and you can collect the teleop trajectories, fairly straightforward. Then you have like a diffusion policy, or you throw it into your VLM, VLA, it doesn't matter. That part can be done. So I've now sort of disappointed you, because I said these are the 3 leading paradigms, and I've pointed to major critiques of all of these. I mean, these are the ones being used, so what's the way forward? So I think there are elements of the right answer in there, but we'll have to do a bit more. So I'll now jump into the kind of approach I favor, and I have to start with quoting Alan Turing. Any computer scientist should quote Alan Turing once in their talk. So this is that famous 1950 paper which proposed the Turing test. Now people never read the paper. If they read the paper, they just read the first page. You have to go all the way to section 6 for this. but it's brilliant. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So Turing was saying this in like 75 years ago, right? 76 years ago. And of course, in the last 76 years, all our colleagues in psychology, child development, they have uncovered a lot about how children learn. And can we get some inspiration from that? So there are many of these techniques in machine learning, reinforcement learning, which were derived from some kind of a formalization of human capabilities. But then after a while, we just work with the formalism and ignore the original. I'm saying that once in a while, it's good to go back to the original inspiration and see if we can pull out some new formalisms which will be more fruitful for us. So this is a review paper from Smith and Gasser. I mean, of course, there are thousands of papers in this business, but I like this because it tries to be crisp and give you like 6 pieces of advice about how children learn, which we can try to think about in the context of machines. And let me just recap, give what each of these means. Be multimodal. So children are like, there's some object, they will bang at it, they'll hear the sound, they'll put it in their mouth, etc., etc. So they're getting signal from vision, touch, proprioception. And in fact, more senses are good because they essentially give you cross-calibration signal. Second, be incremental. So they're like, eventually the controllers have to be hierarchical and we have to build them up step by step. And there's a very natural curriculum that biology imposes on you. Physical, okay, you're learning in your body. So my body is not the same as your body. A child's body is not the same as an adult's body. And what you learn is appropriate for that. There's a lot of trial and error. Search is okay. So Karen Adolph is a psychologist at NYU, and she studies the development of walking in children. So one of our findings is that children fall like 15 to 20 times in 1 hour. 15 to 20 times in 1 hour, okay, when they're learning to walk. And of course, they just get up and start to walk. If you are a parent and you look at them, then they might fuss and cry, but otherwise they do this. Why does it work? Well, they have soft bodies, they have a low center of gravity. I mean, I wouldn't try it for our robots, and I wouldn't try it for our 90-year-old parents or grandparents either. But for a 1-year-old or 1.5-year-old, this works. Social, we learn from others. Culture is transmitted. So, I mean, if I want to be a bicycle mechanic, I don't try to discover everything. I go to a bicycle shop and I become an intern and I learn, right? And then language. Language has a role for the higher level abstractions, which language captures well. So anyway, these are some observations, and now, I mean, we have to convert them to formalisms that we can work with. So I'm going to give you this picture, this single slide, as a way of capturing the thing which I emphasize the most out of this. So if you look at this picture, on the left you have this father and child, right? And the father is washing dishes and the child is observing. So there is some transmission of knowledge which is taking place here. The transmission of knowledge is that you use this sponge and then you dip it in water and then you wipe a surface in a certain way. So, okay, so all that is helpful. The child is observing. But then the child goes and she is playing by herself. The child doesn't have knowledge of the forces, the muscle activations. She doesn't. So some information is incomplete. But that's only part of the problem. Her body is not the same as that of her father, right? So the child has to learn in her own body. And that's what she's doing. And she's playing here. And children do this. I mean, and if you as young kids would have seen this, they just, they play. They observe the consequences of their actions. They're building some kind of a dynamics model of the world. So that's what she's doing. So I like this as a summary or abstraction of what we need to do. Just replace the role of the girl by a robot. Okay. So the robot is going to play the role of the girl, and then the role of the father is going to be played by whatever sources of human knowledge we have, like video clips and so on. So that's the general high-level paradigm. Now let's operationalize this. So I'll give you one example. This is stuff we already did and presented last year at Coral. And this is for perceptive locomotion. So in locomotion, there are these two branches, legged locomotion. One where we are dealing with just blind robots. I mean, 90% of walking doesn't require vision. You're walking on flat ground or whatever, even ups and downs. You can, in fact, the examples I showed you of the robot going up the hills in San Francisco was a blind robot. But sometimes blind robots are not enough. In particular, dealing with treacherous terrain, like stairs. So this is all around central parts of Berkeley. So here, this robot has a vision system, okay, and walks as if it's slightly drunk. But whenever if you talk to your students who have trained an RL policy and it's slightly like this, their answer is always, if I just trained it for a bit more, it would work better. Okay, but now let's get into the science part. The way it was trained was by starting with examples of humans. So we have humans, okay, so these are some of the trajectories collected by grad students, climbing upstairs or sitting on sofas and so on and so forth. And then I'll show you a slide which gives you more of the methodology. So these kinds of cases show up in the training data, but let me be more concrete. So we have, let's say, some RGB video. So this is Arthur Alshire, who's the first author of the paper. And Arthur is climbing up the stairs and coming down. Now we use computer vision comes to the fore. Computer vision has now got quite powerful techniques for doing 3D and 4D reconstructions. So this is the computer vision part of it, where we have taken the human body and converted it into 3D, and over time it's 4D. Then we solve the retargeting problem, because the humanoid is not the same body as the person. So you have to do some retargeting. And then you can't just do open loop replay. You have to convert those trajectories into a policy. So you can initialize something like this, but then you need to actually build a controller, which you can do in simulation by creating variations and so forth. So anyway, that's the general paradigm, and these show you more details. So it's all being done. So in fact, the lifting to 3D or 4D is very nice, because this enables you to initialize a simulator that way, because the physics simulator works in the 3D world, and this reconstruction of the human is and then retargeting is in the 3D world. So there are lots of techniques which just try to do this transfer with pixels, but in my mind, 3D is the right way to go, because then you have a representation which completely transfers to the physics simulator. And that's what we did. And then you can, in fact, get everything out. So you can actually render what the view would look like from the perspective of the robot, et cetera, et cetera. So all of these can be produced. Okay. So just more examples. Okay. So so that's for locomotion. And now let's deal with the more challenging problem of manipulation. So reminder of the paradigm. And so what can we do here? So it's got to be these two parts, right? There's the part which has to do with learning from video, which you have huge amounts of already. And that will capture the kinematics. But to really get robust controllers, you will have to do reinforcement learning in a simulator. That's kind of the paradigm. And this is not done yet. It's not fully done yet anyway. But we have made a promising start, and I'll try to show you what we can do now. So the first part of the problem is the learning from video and retargeting it to the body of the robot. So this is a paper we actually just put out on arXiv today, and so you can find it. But let's look at this. So at the top you have human. I mean, these are frames from videos. And at the bottom, what you have is it's been lifted to 3D. The human hand has been lifted to 3D. The object has been lifted to 3D, and then retargeted, because your human body is not the same as the robot body. So these are static frames, but you can see the correspondence. And then let's see some videos here. So this is open loop replay. This is not a full-fledged controller, but as an open loop replay, I mean, I think this is interesting. And this, to me, is the culmination of decades of work in computer vision. I mean, I've worked in computer vision for 40 years, and we can finally do this. Okay. Okay. It does not fully solve the problem. You have to be clear, because this is just a trajectory, and this will never be robust enough. I mean, lots of people are happy with just trajectories. No, you have to have a controller, a policy. But it's interesting that we can do this transmission, and this is much easier than collecting teleop trajectories. Okay, so these are just more examples. And I mean, this doesn't work all the time. It fails sometimes, it succeeds sometimes. But I think at this point, it's gradient descent. I think we can do this. I think I'm quite convinced. I mean, I've worked on this problem myself for years and years. And I feel right now this we can put out, and it'll get better. And in a few months, in a year, 2 years, I mean, this will be really good. So you don't need to subject some poor people doing this teleop collection, right? Okay. Okay, and then, so these are like some references to earlier work we did, which was fighting this fight. There was also work which was on 3D-fying bodies and hands and so on. One key contribution here was this SAM3D system, which we did with a team at Meta. And this was about how to 3D-fy from a single image. So often in robotics, people make the assumption that you have a CAD model of the object, but that limits your scope. I mean, ideally, you want to have whatever object is there, you should be able to lift it to 3D. Well, this is what the system can do, and here are examples. So you have this image on the left from a single image. We have got all these objects in 3D, and we are showing that off by looking at it from different viewpoints. Here's another example. This is, of course, a famous painting. And here the objects have been lifted. And so why does this work? From a single image, how can you get 3D? Okay, and this is a long story. I've been arguing for this practically for decades, which is that the computer vision has these three central problems. So there is recognition, which we assign names, cat, dog, etc. There's reconstruction, which is classically 3D and people think of as being based on multiple images, but that is only one way of doing 3D. And then there's reorganization, which is others you could call segmentation or grouping. And all these three are interconnected and help each other. And I'll give you an example. So let's look at this. We are doing reconstruction. So you look at that area which is outlined with a thick green marker. So from that we reconstruct on the right. So what are you doing here? You obviously do not have enough data for the 3D shape of an elephant from multiple views if it's a single view. No, you're just doing recognition. Once you have recognized that it is an elephant, you hallucinate the rest, right? And the same is true in the second row and so on. When you are a child and you're growing up, you develop models from multiple views. But when you're an adult, you guess and complete. Okay, that's what we're doing. These are more examples, right? So basically what is needed here is that you've solved this giant supervised learning problem, which is that you have example images and then associated 3D models, and then you do the reconstruction, right? So there's some details here. I mean, there's some usual architecture with some usual mumbo jumbo. But the interesting part is actually how you train, how do you get the data? Because humans are good at saying this is a cat, this is a dog. They're not good at reconstructing a 3D model. There are a few people who can. These are the graphics artists employed by Hollywood, but regular people are not. So long story here, which I won't get into, but it turns out that humans can be used to judge which of two 3D reconstructions is better, and then you can bootstrap that, and we did, and that's all the details are in the paper. Okay, so that tells you how we can solve the first stage, the left part. I mean, again, I don't want to assert that we have solved it fully, but I think we have bit off a substantial chunk of the problem that I'm confident enough that in a year, whatever, 2 years, some relatively short amount of time, this could become really good. And even if it doesn't become good for all videos, even if it is good for 50% of the videos, we can just use those as training data. Okay, so now the second part. So the second part has to do with training in simulation. And here, what the girl is doing when she is playing. So here, I think this is where it's at now. And we are working on this, and this is not a solved problem. But I see no reason why it won't be. Because we solved all of this in the context of locomotion. So the so-called sim to real gap is an engineering problem. We can solve it. Okay, I think the problem of reward specification becomes much easier when you have this human trajectory defining the task. So you just make it a tracking problem in some sense. So that bypasses the challenge of engineering 150 terms to specify the task. So that goes away with the human trajectory, and now you are left, you're going to train in a simulator and then put it in the real world, and you have to fight the good fight. And I think it is totally winnable. I'll show you some vignettes from my work that I was involved in, but I think this is work in progress. So here is some work which is led by Torulin, where you're training some humanoids and doing various kinds of tasks. And there's and these are published papers, and not just in my lab, but others. So these are examples where trajectories are being trained. And let me show you different tasks. There's some generalization, and then robustness. Yeah, the obligatory, you try to disturb the thing. See, you won't get that if you just do open loop, collect trajectories and do open loop replay. Okay, you have to have a controller, that's why you need the physics model. Okay, now with these physics models, you can either hand design controllers or you can do reinforcement learning in a simulator, but it always falls in the classic control paradigm that you have a dynamics model which enables you to build policies. So I believe in that. Now let me get a little bit to the lowest layer, which is about tactile and proprioception and forces, just a reminder. So this really requires actually building the sensing technology. See, for computer vision, the sensing problem is solved. I mean, there are 10 billion people on the planet are roaming around with a camera in their pocket, right? So when I started in computer vision in the early 80s, we used to have 3 images which everybody in the field used to work on, because we didn't have digital cameras or any such thing. Well, tactile is not as bad as being 40 years ago in vision, but the situation is such that the sensing methodology needs to be developed. And this is a project out of Meta, which was developing a very fancy sensor, which kind of was, in fact, better than humans at the measurement of various kinds of normal forces and shear forces. This enables one to train policies. So this is a policy trained in simulation, but the fingertips here have tactile sensing, and again, trained in RL. But this slide is the important one, which shows that that if you only have proprioception, you do have a performance which is at the left. If you have true ground truth shape, that's on the right. But and then the second and third columns correspond to just vision and just touch. And then if you use the two of them together, your performance goes up. I mean, it's common sense, but it's sometimes common sense is not so common. I mean, almost all robotic systems today are designed without using touch. In my view, this is silly. I mean, So of course, there's a challenge, which is that the hardware isn't quite ready. So you have to work with experimental hardware, but we cannot be scared of that. In fact, we have to use those sensors, develop policies, and then this will create there's a push-pull for the development of technology. More people will work on tactile sensing once there's been downstream work showing that it is important. So this is another project. This one is based on using sharper hands, and this was an early version. So sharper hands is one of the hands which is on the market, which actually has tactile sensing, multi-finger. And we are doing various tasks like peg insertion, cap twist, etc. So for some of these tasks, you really care about forces, right? Insertion task. You don't want to do it with just position control. You want to look at forces. And again, the details are not so important, but all this, what the slide shows is if you use tactile and you use vision, you're better off than just using vision. So there are three main senses which we should be using. Use vision, use proprioception, which is all the joint angles, and then use tactile. And in particular tasks, the mixture will vary in terms of how much it matters, but in general, you got to use them all. Okay. Okay, and then I want to have this slide which shows a little bit about why that reinforcement learning can be in simulation and it can be in the real world. Now, in the real world, the advantage of that is that now you don't have the sim to real gap. But of course, if you directly try this, your robot hardware will break because the search is huge. So, but once you have trained a policy in simulation, it's kind of working at the 90% level. You can do all the fine tuning in the real world. And this is an example of that. And you can give feedback. A human can say, this is good, this is bad, and so on. So I'll move on to like a couple of summarizing remarks. So I'm a big believer in skills, and this skills is not the same as skills in the context of your Claude model. I have this slide from years ago before we had Claude skills. And for me, the goal is a 5-year-old child. A 5-year-old child, a 5-year-old human child has amazing dexterity. They can grasp objects in many different ways. They can this is the stage where they can learn to write with a pencil. That's why we can send them to school. Sooner or later, they learn to button their shirt and they can tie their shoelaces. I mean, this sort of stuff. So I want to focus on those simple skills and get them right. It's very important to have generalization and robustness. Okay. Generalization comes from pattern recognition. We don't accept a cat recognizer if it recognizes exactly one cat from one viewpoint. It has to work across. So if I want to be able to pick up a coffee mug, I should be able to pick up any coffee mug. It should work across locations. So you should generalize across position. It should generalize across, so these are the three generalizations I care about. Across category, across location or pose, let's say, and then background. The background clutter should not matter. The lighting should not matter. Again, many systems that we see these days, they fail one or more of these tests. What we have got is a very narrow memorization of a certain capability. So, okay, generalization, robustness, I am referring to more the control theory type of sense of this. And this is where you need a controller. You're not going to get away without a controller. How do you solve a more long-range task? You have to do it by composition. If I'm thinking about how to get back to Berkeley tonight, I cannot do this at the level of muscle activations. It has to be at the level of Uber, plane flight, Uber, then getting to the Uber is walking up the stairs and obstacle avoidance, etc. So there's a hierarchy and compositionality. These are classical ideas which should not be forgotten. I think this will be necessary. I'm making a religious statement at the bottom, which is that multi-fingered hands with tactile sensing will be necessary. And I am about to conclude, but I will put in an advertisement of a paper. This is more like a position paper or a philosophical tract or whatever you want to call it. This is with Emmanuel Dupont, who is a cognitive scientist, Jan LeCun and myself. And we are critiquing the current dominant paradigm of LLMs will solve everything. And here's a picture. The LLM machinery is not vanilla learning. There are actually armies of engineers curating the data, and there are these cleverly designed stages of training, etc., etc. So it is a major deviation from the spirit of learning that you don't build in stuff. Lots and lots of stuff is being built in. Humans learn as in this other way. There's autonomous learning. You come with some genetic endowment, you have your experience, you're doing experiments in the real world, and that's how you learn. And we have tried to model it with the system A, system B, and M. One A system, something like unsupervised learning, which is observing the world and building a model of it. And then there is a part which is acting in the world, which is closer to sort of the spirit of control and RL, and then some orchestration. And I will leave you with this summary slide of the high-level view of how robotics should be done. Thank you.
Perfect. Thank you very much. Let's take some questions. I think go to the mics if we want. We'll pass them around. But we'll start here at this mic.
Yeah, thanks for the very interesting talk, Jitendra. So you brought up the issue of data in robotics, correctly, and you gave us a promising pathway for how to actually collect this data in a way that can solve manipulation. Where do you see the role of models, especially dynamics models, since we're in L4DC? Is it only at the level of simulation to have good enough simulation, perhaps for that step of the trial?
Yeah, in this story, this is the place where, so like I had this picture of this girl and her father. So the one on the right-hand side, when she is trying to develop a policy with experimenting in her own body, that is the role of a simulator. But a simulator could be a physics simulator, a simulator could be a learned simulator, those models. So there could be models at varying levels of abstraction. So the lowest tier always is back to F equals ma or something, right? But I'm not necessarily operating at F equals ma. So if there is an object on a table and I'm pushing it with a finger, and like if I'm playing maybe there's some game in which that is involved. Well, I have a kind of model of where to poke this object with my finger, which I've acquired probably when I was 3 years old from actually having played. So we don't have so we actually have zillions of models based on our experiences interacting with objects over the years. And that collection of models is what you need to acquire. Now you can acquire them from first principle reasoning in a physics simulator, but I think that when you're a grown-up, you don't do first principle reasoning. You've already got that compiled higher level model. And this is a standard tradition in physics, right? In physics, you have models at differing levels of hierarchy. I mean, the models of optics, for example, I used to do a lot of computer vision. I mean, ultimately, you can say they come down to Maxwell's equations and electromagnetic radiation interacting with a surface. But you don't really operate at that level. You have this abstraction of a Lambertian surface, things like that. So I think that we need, in the world of mechanics, the same kind of abstractions that we had in the world of optics.
Did we have somebody over there? Yeah.
Thank you for the very interesting talk. The question I have is around the aging of the robot itself. So, first time when the robot comes out of the factory, all the motors are not going to be identical as what they had at the time of training. And then over a period of 10, 15 years of that robot's operation, the motors and actuators and everything is going to undergo some sort of degradation. So is that something we need to be worried about at this point of time in order to build the policies, or is it something that we don't have to worry about?
Very likely your robot will not last 15 years. It will last 6 months. But that's
until
a
the end of warranty,
answer.
I guess.
No, but my serious answer is that you should always be recalibrating. And when you're doing sensory motor, you can actually do that because you always have measurements. Sensory measurements and actions and the consequences of that. So that's a loop we can always do. So with humans, there's this ability that if you put a prism in front of one of my eyes, then all the rays are deflected by 10 degrees. So when I try to reach out now, I'm going to be off.
Yeah.
But I just keep doing this task for a little bit and my system gets recalibrated. So we have a couple of papers on this. So the answer is there should be continuous lifelong recalibration. And this is what, of course, children do, right? Because as they grow, their bodies are changing. The distance between the eyes is not constant. So the stereo system has to recalibrate, et cetera, et cetera.
Thank you.
Thank you for your talk and sharing your insights with us. So I had a talk about a question about human walking. In your example, where there was 3D reconstruction and you're trying to imitate and then design a controller around to give robustness, it seems that everything was learned, but in humans, there are these primitives we have coming from the central pattern generator that we build upon to learn. Is there a role for having some sort of very well designed and engineered primitives and then learn on top of those? Or in your opinion, should everything be learned from scratch?
I'm not religious about these things. I think I'll speak specifically to legged locomotion. If you consider a cockroach, right? It's probably not a learned controller. I mean, even like a mountain goat can walk pretty soon after being born. With humans, it seems to be largely learned. And there's an interesting finding there. When a child is born, then the child can move their legs. So there's probably a leftover from evolutionary time CPG in the system. But it's not effective. The child at 0 months cannot walk because they just don't have the muscle strength. And then when they learn to walk at the age of 1 year, it's much more learning in the case of humans. But across biology, there is kind of a mixture of hardwired and learning. So I'm not religious about these things. I think.
All right. Thank you.
Perfect. So I think we're at the limit for the session. So thank you again.
Thank you.